Okay, hopefully a quicker video this time, but knowing me, I'm promising nothing. We'll see how we get on. So crowbar is used to remove a nail, so we've got a crowbar here, that's this yellow thing. Someone's pulling on this end with a force, and this crowbar is going to be a rigid body. And we're going to, here I've sketched a very rough rigid body diagram, so a free body diagram, sorry. So we've got the free body diagram here. So we're just thinking about this and what forces are being applied to it. So there's someone pulling this way, so we've got a force this way. At the other end, the crowbar is pulling a nail up, but we've got to think about what forces are being imposed on the crowbar. The nail is trying to pull that crowbar down, and so the force that the nail is exerting on the crowbar is in the downwards direction. So just before this nail starts to pull out, or if you're pulling this nail out with constant velocity, then you've got a static equilibrium situation. So we can use the static equilibrium rules. So that would mean, let's just write them again so we see them 1,000 times, you'll remember them. So sum of f of x is 0, sum of your x components, sorry, should be 0, sum of your y components must be 0, and in situations where the forces don't all converge at one point, the sum of the moments must also be 0. So we could have used that, the question hasn't asked us to do that, but we could have used the sum of f of x and sum of fx and sum of fy is 0. We could have used that to figure out the reaction, but we're not doing that in this case. But it'll be somewhere, let's just suppose it was vertical. I just want to have a look and see if they do actually converge. So they'd have to converge within the rigid body itself. And clearly we're not getting these forces converging at one point. A little bit better. I mean, these aren't even really, but just roughly anyway, we can tell. So you're getting a couple of points where it crosses. So there's an intersection here. So they're not all crossing at the same point. Therefore, we also need to use the additional rule that the sum of the moments is equal to 0. And it's the sum of the moments that equals 0 that we're going to use in this problem. We haven't been asked for the reaction. So let me just rub all this stuff out quickly. Take that away, put my force back. Now this problem is very similar to your seesaw problems, and so what you could imagine is if you, in terms of moments at least, not so much in terms of reactions, but you could just imagine this being straightened out. You'd have a force down here, a force down here. So essentially you're going to have a big force or a big person at this end, close to the support, and you're going to have a tiny person at this end, far away from the support. And the moments of those two forces are going to balance out. So what does that mean? I think we've talked about this before, but it means that you're going to apply a small force. If these two moments balance, then it must be a relatively small force at this end produces a very large force at the other end. And we'll get to in section C that where a mechanism takes a small force and makes a big force is called mechanical advantage. And so the ratio of these two forces is called the mechanical advantage of the system. It's a bit of an old school term, but people still use that. So let's work through the question. What's the moment of the force about A? So I think it's talking about force F1. It's saying a force F1 of 350 newtons is applied at the handle. What is the moment of the force about A? And so we have got moment is equal to force times distance. Why have I left a space there? Because I'm going to think about the sign. So this force is going to tend to want to pull this crowbar anti-clockwise. So if we look over at the free body diagram, this force wants to rotate that crowbar anti-clockwise. So it's positive. And so I didn't need to leave a space after all. Let's move it back. So therefore, moment is force times distance, and it's going to be positive, which is equal to force 1, we'll write it out, force 1 times 0.3 meters. Force 1 was equal to 350 newtons, so it's 350 newtons times 0.3, what's that going to be? So it's going to be, one thing that's a good idea when you're doing engineering calcs is just try and estimate the result in your head so that you can check what you do in a calculator. So if we were to do 350 times 2, that would be 700 newtons plus another 350 would be 105. We'll divide it by 10 because it's not 3, it's 0.3. So it should be 105, 105, something like that. So let's just check it. So 350 times 0.3, 105. So that's going to be 105 what? 105 Newton meters. So another quick check. This is less than a meter, so the moment must be less than the force you applied. If this force was applied at 1 meter, then the magnitude would have been 350 Newton meters. In our case, we've got about a third of that, so it's about a third of the force. Sorry. So where am I going to write it? I'm going to write it along here. Moment of F1 about A equals 105 Newton meters. Sorry about that, I can underline it. Okay, B, what's force F2 that's getting applied to the nail? So what rule are we using? The sum of the moments must be equal to 0. So therefore, we'll call it M1 and M2, relates to F1 and F2. So M1 plus M2 must be equal to 0. We already know M1. M1 is equal to positive 105 Newton meters. M2 is force times distance, which is equal to F2 times, this time the lever arm is 40 millimeters, so the distance from this force to that support point is 40 millimeters, so that's 0.04 meters. So let's substitute those in now. So M1 is 105, so M1, 105. So, oh, be careful. So M2, what have we forgotten, or what have I forgotten? I've forgotten to check which direction that was in. So this time it's that force, if you think about your free body diagram, this force here is going to try and rotate the crowbar in this direction. So that's clockwise, so that's negative. So therefore I should have had negative, negative. And you should really, let me tidy this up, you shouldn't have your units in there, and you should probably put the 0.04 first. 0.04 F2, and it's in the negative direction. So 105 Newton meters is what M1 is, plus M2 is minus 0.04. So if you add a minus, you get a minus. Minus 0.04 F2. Ugly, ugly. Fix that. F2, which equals 0. So the moments have to add up to 0. Therefore, minus 0. Well, what do we want a minus? So what I'll do is I'll take this across to this side, and then I'll swap the sides. So we're going to get 0.04 F2 is equal to 105. Therefore, divide both sides by 0.04 because it's times in the F2. 105 divided by 0.04, which equals, that one I'm not so good at doing in my head. 10th would be 0.1, so a 20th of that. Roughly speaking, it's going to be somewhere near times by 20. So it's going to be 2000 or something. Let's have a look. 105 divided by 0.04. So 26,025. do I change it to kilonewtons? Probably not. Everything else has been in newtons so far. I'll just leave this in newtons as well. But I'd probably round it to 3 significant figures. So 2, 6, when it's a 5, I round it to the even number. Different people do different things. 2620 newtons. And I've kind of done it in my head, so it looked about right. So therefore, where was I? Right, the answer. Force F2 is 2620 newtons. So let me just quickly check that. So we double check. I'll just do it backwards. So it's 2625 times our lever arm was 0.04 should give us the moment, which is 105, which is what we had before. So just a quick check on that. Sometimes if there's no other way, you can just check things by doing them backwards. C, what's the mechanical advantage of the crowbar? So mechanical advantage, C, is just how much you multiplied the force. So we just take F2 divided by F1, which equals 26. I'll do this, I'll keep the answer to 4 significant figures in this calc, and then I'll round it to 3 at the end. 2625 divided by our initial force, F1 was 350 newtons, divided by 350, which is equal to, oh sorry, wrong one, I've closed it. So much for a short video. So we've got 2625 divided by 350, was it? Divided by 350. 7.5 is the mechanical advantage. 7.5. Mech for short, advantage is equal to 7.5, and it doesn't have any units, it's just a multiplying factor. Now, it should be the case that that is the ratio of the lever arms, so that's one way we could check it. So when you've got a lever, the mechanical advantage is just the ratio of the lever arms. So we could check that by just saying, so the long lever arm was 300 millimeters, the short lever arm was 40 millimeters. So we should be able to calculate a check on that. 300 divided by 40, 7.5. So we checked our answer. That's that one. Okay, so we've got a few ideas. Now we're just going to talk about some little wrinkles you have to be aware of when you're thinking about these problems in terms of the angle of the force relative to your point of fixity or your support point. So let's have a look at that next.